Hi all, today we discuss the examples, illustrative examples of theorem 7 and 8. First we discuss example 18. We start with the field F and alpha is an element of Fn. Fn is a vector space over F and this alpha can be written as alpha is equal to uh, x1, x2, etc. xn. Then clearly you can write it as x1 times 100 plus etc. plus xn times 00001. So this shows that this is equal to x1 epsilon 1 plus etc. xn epsilon n, that is the coordinate of alpha relative to the basis b is equal to x1 x2 etc. xn, where the basis b is the standard ordered basis epsilon 1 etc. epsilon n. So this is what we discussed in example 18. Now we have example 19. In this example, we start a matrix P. P is cos theta, sin theta as the first column and minus sin theta, cos theta here. So you can easily verify that this determinant of this matrix is cos square theta plus sin square theta, that is equal to 1 always for a fixed real number theta. So this P inverse can be obtained by, since the determinant is 1, you can take just the adjoint of this matrix, that is cos theta here, and we have minus sin theta and sin theta. This is the inverse of this matrix P. In fact, what is the relevance of this matrix? Once you consider this standard basis epsilon 1 and epsilon 2, and you rotate this epsilon through an epsilon 1 through an angle theta, you can say that this length is nothing but cos theta and this will be our sin theta. So you can represent that the resultant vector obtained by rotating this epsilon 1 as cos theta comma sin theta, and when you rotate this epsilon to theta degree again, so you can get this as theta degree. Then this is what we call the new resultant vector. Then this vector can be obtained by taking, since this is theta, then this is 90 minus theta and this will be theta. So you can say that this is our sin theta and this is cos theta. Now you can represent this vector as minus sin theta comma cos theta. Okay, so when you consider this P and a standard basis and evaluate P times epsilon 1, that is P multiplied with 1 0, that will give cos theta and sin theta. So that is the vector cos theta sin theta. Similarly, when you evaluate P epsilon 2, you can get the other vector as minus sin theta and cos theta. So these are the P epsilon 1 and P epsilon 2 are these two vectors. This is P epsilon 1 and this is P times epsilon 2. So the action of this matrix P is nothing but the rotation of the axis. Okay, so the rotation of every vector in R2. So this P can be considered as a rotational matrix. And using this P, since P is a non-singular matrix and epsilon 1 epsilon 2 are standard basis, we can say that these two are again a basis for R2. Say B prime. B prime is the ordered basis. The first element is cos theta sin theta, and the second element is minus sin theta cos theta. These are the vectors in the new basis B prime. Now, in the previous example, we have seen that if alpha is equal to x1, x2, we can say that the coordinate of alpha relative to the basis b is the standard basis, equal to x1, x2, where b is our standard basis epsilon 1, epsilon 2. Now using this x1, x2, we can find the base, these coordinates of alpha relative to the basis b prime constructed using this p. So that is actually that is equal to x1. Instead of x1 we have x1 times, that is p inverse times this. So that is obtained by uh, cos theta sin theta minus sin theta cos theta times this x1 x2. This is because of theorem 7. In theorem 7, we have proved that alpha relative to b is equal to p times alpha relative to b prime. So this coordinates can be obtained by multiplying this coordinate with p inverse. So this is p inverse. So you can write it as this is our x1 prime and x2 prime. Those are the coordinates of this alpha relative to b prime. So that is obtained by multiplying this. So that will be x1 times cos theta plus x2 times sin theta, and this is minus x2 times x1 times sin theta plus x2 times cos theta. So these are the new coordinates. Now we have example 20. It starts with the field f, the subfield of complex numbers, and matrix P is equal to minus 1, 0, minus 1, 4, 5, 0, 2, minus 3, 0, 0, 8. You can verify that this P is an invertible matrix with the inverse, this matrix. By multiplying, you can verify it by multiplying these two P inverse. That will give the identity matrix. Then once you multiply this P with epsilon 1, you can get minus 1, 4, 5, 0, 2, minus 3, 0, 0, 8. Multiply it with 1, 0, 0. That will be the vector minus 1, 0, 0. Similarly, you can find p epsilon 2, that will be this times 0, 1, 0. So that will give 4, 2, 0, and finally p epsilon 3 will give the corresponding vector 5 minus 3 8 by multiplying this with 0 0 1. So these three vectors form alpha 1 prime, alpha 2 prime, alpha 3 prime. Then if you consider the coordinates of this alpha with respect to these basis vectors as x1 prime, x2 prime, x3 prime, and the coordinate of alpha corresponding to the standard basis vector is x1, x2, x3. So that we have shown in example 18. If alpha is this one, then the coordinate of alpha relative to the standard basis will be x1, x2, x3. Okay. So once you got this one, you can find the coordinates of alpha corresponding to b prime as this matrix times this one. When you multiply these two matrices, you will get this one. Okay. Then we can say that when you consider this 3 to minus 8, that is equal to minus 10 alpha 1 prime minus half alpha 2 prime minus alpha 3 prime. That is, when you replace this quantity alpha by 3 to minus 8, then evaluate these coordinates. So you can get that as minus 10, minus half, and minus 1. So that these are the coordinates of this 3 to minus 8 relative to the basis b prime, that is alpha 1 prime, alpha 2 prime, alpha 3 prime. With this, we can wind up section 2.4. Then next session will be 2.5, and in the next lecture we will discuss section 2.5.